So my name is PJ Kirner. I'm the CTO and one of the co-founders of Illumio. How I wanted to start today was, again, to lead you into the announcement is how did the Illumio journey start for a second? So there are three major technology trends that I identified, early on. So number one is this idea of dynamic compute, right? And if you think about, 15 years ago, you used to get the compact catalog out or the deck catalog out, decide what servers you wanted, and order them, and they would show up like months and months, on the pallets and get racked and stacked, and there was a slow delivery of compute. You have VMware sort of accelerate that. AWS, where now I can have a credit card, and if I want a whole compute farm, I can get it in minutes. Right? And you have the rise of containers, right, where containers can sort of live for sub-second intervals. So there is this change of more dynamic compute. Second trend was the idea of distributed systems. If you sort of think about the old architectures, you'd have a three-tier architecture. Things would come in the top. They'd hit the web tier, go to the app tier, go to the database tier, and then sort of back out. Back out to the internet. Today's architectures are more of the microservice variety, where solving a single application is going to talk to a whole bunch of applications to be able to assemble the answer. I mean, the extreme, as I said, the extreme point is a full microservices architecture like Netflix delivers, where one web page is really thousands of applications sort of there to sort of deliver the content, right? And the third trend is the lateral movement being a risk. And so Wendy talked about the dwell time, right? There's many different statistics about how long bad actors sort of stay in your environment. But they're all, whatever the number you sort of have, they're all in the hundreds of days that these bad actors are sitting there. Well, what are they doing? They're harvesting credentials. They're looking for data. They're looking for the good assets, right? They're moving laterally inside the network, right? And part of this is like the evolution of networking and these flat networks that sort of appeared, and that becomes a risk, right, to those environments. And what you need to solve that risk is a micro-segmentation strategy. So in terms of our architecture today, before I sort of introduce the supercluster, I just want to sort of baseline people with this. So it's a full 100% software delivery. So everything I'm talking about is software. There's no hardware involved. So the first point is the virtual enforcement node. And the virtual enforcement node is an agent that gets installed onto workloads that you have, whether they be in traditional data center environments or into cloud environments. And this kind of acts like they act like an antenna. So we support things like Windows workloads and Linux workloads and Solaris and AIX. And really, we had the theory of you need to be able to install these agents anywhere to collect any information in any environment. That was part of the founding thesis. So what did they do? They act like an antenna. And there's the second part of the software architectures, which is the policy compute engine, right? And the policy compute engine is the brain of the system. So the first thing that happens is what these systems do is they transmit a lot of context and telemetry. There's a lot of network flow information, information we get out of the hosts, like process information. A lot of all this context and telemetry is sort of sent over to the PCE. And that PCE, the first job it's to build a map, right? It builds a map of your data center applications or your cloud applications. Who is actually talking to who in real time, right? So you and we call this the application dependency map. So you understand, how these applications work, because you might not have ever seen how they actually communicate, right? Your application owners might not know. They installed some software and things sort of work. They might not know, right? So building this map allows people to sort of understand what their application topology is, understand how connected they are. And people are surprised when they sort of see these maps for the first time to see how, again, how connected their application environment has been, and then how much risk is, associated there. So that's the first step. The second step, if you're doing a micro-segmentation strategy, is to have this plain language policy, right? And so one example I'm just going to use very simply is this. Let's say you want to have the dev workloads talk to, all the dev workloads talk, and all the prod workloads talk, and maybe you have some production, you have some exceptions to allow prod to talk to dev, right? That's a very simple way you can describe the policy, and that's how you actually use the system. And Matt will be demoing the product later. He'll sort of show you some of these things. But you write this in a very kind of plain language, the way you sort of talk about these things. what the policy compute engine's job is to figure out how, like, what are the necessary instructions. You can think of it like a compiler or that. All the necessary instructions to implement and execute that high-level policy. And those are all pushed down back into the VENs, right? Back into the VENs. And then these controls are sort of implemented in terms of IP tables, if you're typing Linux or Windows filtering platform or some of the other enforcement points. So we don't do the enforcement. We sort of program and instrument other enforcement points that you already have that exist. So that's kind of the micro-segmentation architecture. Also, this past year, we introduced something called vulnerability maps, right? And what that does is we take third-party vulnerability information and overlay it on top of that application dependency map. And what that allows you to do is, number one, it sort of it contextualizes your vulnerabilities. So for example, let's say you had a high vulnerability that was constrained inside a segment, and it had very limited network connectivity. Right? At that point, that's probably not a high priority to patch. Let's say you have a medium vulnerability, right? One that has broad access to your entire data center. That might be a better, a higher priority to sort of focus patching efforts. So having this extra contextualization on given your micro-segmentation and traffic allows a security team to better decide where to do that. In addition, we can provide vulnerability shielding, right? Basically apply a micro-segmentation policy to limit the exposure or basically block those things off. So both the vulnerability map, the visibility allows you to prioritize as well as the prevention capabilities. So that's the architecture that we have today. All right, and this is what we've been shipping for 4 years and what our customers have been buying. So the one other kind of critical point is, like, we sort of believe that you already have all the sensors and enforcement points that you ever needed, and you just haven't had a way to sort of activate them, right, and control them. So what I sort of said is, whether it's IP tables or we have controls of F5 load balancers or Cisco and Arista switches, have the ability to sort of program and orchestrate all of those kind of enforcement points and collect data from them is what Illumio sort of does, and what our platform does. All right, so okay, now back to what are we introducing, and I'll tell you how we're doing this and some of the architecture components. Right, so fundamentally, the PCE Supercluster architecture is a federated security control plane that supports 100,000 workloads. Right, those agents sort of deployed in data centers. Right, and it's we believe it's the first kind of global security policy and real-time application dependency mapping. Right, that's what we're sort of delivering. And let me tell you about why I think it's necessary and what the problems are. So if you sort of think about this for a second, when you had one data center, and I'm just going to use the firewall as an example. Like when you had one data center and you had a few firewalls, you probably just synchronized those things, and you program the CLI, and they both at a small scale those kind of worked, right? If you sort of go to a couple of data centers, you probably have a central sort of management plane, right, that would allow you to sort of orchestrate those things. But when you're talking about the large customers, and as Wendy said, a lot of large financial institutions are customers of ours. When you're talking about that scale, right, and those kind of problems, you have to have a different approach, right? And this is where customers need kind of a global security control plane, a global security policy, right? So why is this problem getting worse? Number one is, and this was I was hinting at before, is applications in the past didn't always need global connectivity. But as time goes on, these applications are getting more and more connected, right? Being able to sort of have a security policy that works across all of these environments as a single environment is critical to solving these problems. Number two, at the global scale, you might have high availability for a single region, but these large organizations need to solve the geographic disaster recovery problem. So if, like the East Coast, if there was a true disaster where you kind of, you lose the East Coast, you have to have a way to operate, right? And that operation requires that you are actually able to stand up, those same applications, in a different geographic region, right? And to be able to do this, you need to have a global security policy to be able to achieve those, achieve some of those goals and still stay secure. And the third thing is, what we see more is there's regional requirements for application deployment. So you might have GDPR, right? You might have single country requirements where you actually need to stand up the exact same thing in multiple places, right? So why would you not sort of leverage a single kind of global security model to sort of be able to do that effectively, as opposed to have to do this multiple times? So those are the three kind of things, right? So let's talk about why other architectures fail, right? So if you do have a single centralized system, right? And this is where we started. We started with a non-federated single system. Ultimately, you get to a point, and this is where our customers, this is like demand from our customers have pushed us to deliver this, right? But at a certain point, it won't scale, right? Centralized systems have limits in terms of scale. Secondly, I talked about all of this, all the data that's coming back. Right? If you're really building a map of your data center, bringing all the data back to one place is going to have an impact on international WAN bandwidth, right? And then third thing, the third driver that we sort of have is not security and not operations thing, is the risk people come in and say, well, you can't just put all your eggs in one basket, right? You have to have a different architecture. Secondly, okay, let's say you did a single centralized system and you got so far, but then you decided to do this. It's like, okay, well, I'm just going to set up multiple control planes in multiple places. So what are the real challenges behind this, right? So what you're doing, if you deliver a solution like this, is really putting the burden of synchronization on your customer, right? If you have multiple workloads, multiple policy objects, right? And if you believe what I sort of said is that the world is getting more and more global, right? These things are getting more and more connected. That means you're putting these things in multiple places, require that they are done correctly, require that they're synchronized properly, and you don't have any sort of human error. And those things can lead to right? Then you have the problem of cross-flow, cross-region flows, right? And how do you sort of deal with that? Well, the person on one side has to program the outbound side, and the person on the other side has to program the inbound side to actually be able to make this work. You've got to synchronize that. So why push all these things onto your customers? And then in terms of the map, right? I mean, what are you just going to say? Like, if you just have multiple maps there, how do you sort of knit them together, right? To provide kind of one global view for somebody who's trying to use the map to, discover something or understand the operational issues. Those are the reasons this architecture does not work. Right. So back to what did we build? Right. Again, the PCE Supercluster, is a federated security control plane. So all of those things all work together as one system, delivering global security policy, all those things we talked about before, micro-segmentation, and providing that visibility at scale. Right, we designed this, for our largest customers, right? For global enterprise reliability, both, HA being, a local survivability, and DR, global survivability, and we built it for, enterprise scale. Right, and again, the last thing is this is not a launch of we had an idea. This is not a launch of our developers are just finished coding this afternoon. This is running in production today. Actually, the next live deployment is going to go live in production next Saturday. So that's where we are. So let me reiterate some of the benefits, right? So some of the benefits of this architecture are simply broader width for policy updates, like being able to solve all of these problems and being able to do it with more control planes, being able to push the data out to a larger number of workloads. That's a simple one. The other one, this one's a little more subtle, is people do this being local versus global balanced, right? Support this idea of global connected applications and this need for global connectivity, combined with being able to optimize for applications and application changes that sort of live locally in a specific region. Right? Because you don't want every small change to need to propagate everywhere to sort of solve this problem. You sort of have to strike this balance between global and local solutions to the problems. Secondly, it just gives people better flexibility of where they want to put these control planes. Right? Back to I sort of said there might be reasons to put them in in specific regions, or for there might be other drivers, and you now have the flexibility to be able to do that. Obviously, central configuration, all the configuration that we sort of provide is sort of fully propagated. And what this another point, well, this could be obvious, but it's worth stating is we have this. The architecture allows us to have a separation of the security model and how you do segmentation independent of the actual infrastructure doing that. So this continues with that architecture, and then allows you to sort of support some fault isolation. So let's get to a few pictures of sort of how it works, right? So number one, so let's say these are 3 regions that you sort of have. One in Asia, one in the United States, and one in the European Union. One is defined as the leader. And that leader is defined as the master for the policy model. The policy model is kind of replicated out, right, to each of the members. So they have copies. They have copies of it. But this goes back to that global versus local. The member over here is the master for all of the workload data. All that information about whether it's the IP addresses or the network flows or all the processes that are running sort of stay kind of local to stay like this becomes stays the master for that data, right? And those things are replicated to other environments if they're needed for policy computation. Now, if you were to sort of make a change to policy, right? That provision comes through the master node, right? That gets replicated out to the necessary environments. But then all of that, remember I talked about the idea of the compiler, right? Being able to sort of take that high-level policy, and dev can talk to dev, prod can talk to prod with some exceptions. Like that is a relatively simple kind of statement. And you can imagine that's not a large number of bytes to be able to replicate. But the necessary implementation, which IP addresses and can actually talk to each other that make up these different sets of data, that's what we call the policy perspective. And those are calculated locally. All that work is done in each of those regions. I know it's just there's one arrow there, but all those zones are a region to be able to sort of implement that.
So do you have only one instance of the PCE in each region, or is there within that region, do you have multiple instances within the cluster that is in charge of sharding between workloads?
So yes, there is, and in a few minutes, there's actually a picture that will show you what the breakdown of how to actually have high availability and what the architecture of a PCE cluster is. And so yes, there is, but the picture will tell you better.
Perfect. Thank you very much.
Let's say there is a policy in Asia, and now another policy is coming from the master location, which is United States here. Is there one preferred one? Like local one is preferred always, or global one?
So first of all, we have one thing I haven't mentioned was we have a whitelist model, right? And one of the benefits of the whitelist model is that rule ordering is not a problem, right? Because you sort of express who is allowed to talk as opposed to who is not allowed to talk. Because if you think about a traditional kind of firewall, for example, is you have the problem of you have a block rule, you have a deny rule, and then somebody changes the order, and then all of a sudden you can't figure out what's really sort of happening. So we have a model that's a whitelist model, and we have the idea of exceptions. Like you can put holes in things, right? To sort of solve some of these problems, but it's a whitelist model. So adding things is trivially easy. But to sort of answer your question specifically, I mean, it's really kind of the U.S. The rights for new policy comes through the leader.
Mm-hmm.
Let me just understand something. So it's clearly agent-based, right? Yes. So I guess every host needs to have that. So do you do an application discovery first to do that? What is
application dependency map, I think.
So yes, it's agent-based, right? What people normally do is they roll out agents, right? So if you have Chef or Puppet or a highly automated kind of infrastructure, you can sort of roll out agents. The agents initially sort of just sit in data collection mode, right? That's, if you remember the slide, it's just collect all that context and telemetry, understand who is talking to who, and build the map, right? So this is well before you get to policy, right? Any policy writing is you're really just in mapping mode, right? And people stay there. Like people stay there, try to understand what's going on, and sort of build that map.
Map is not dynamic as things change? Or?
The map is definitely dynamic as things change, right? So it updates as things go on. As they get new flows, as you add new agents, that happens, yep.
Can we have multiple leaders? Like, for example, maybe I have multiple data centers in Asia, and one Asia master or leader and lots of other members, and then global masters like US here. Can we have like that?
So what we do have, so no, we don't have that, but what we do have is we actually have a relatively mature RBAC model, right? So understanding, so you can actually give permissions to author policy for subsets of workloads, and I think we'll sort of see this in the demo, like to different kind of owners, right? So you could give the ability to write policy to Asia Data Center 1, and then give that to a set of users, and then a different set of users you could give the authority to write that policy. They still all would become through the leader, the API calls.
This is very good actually for RBAC. Like it's also providing privacy, and it immediately reminds me like a BGP hierarchical RR. So yes, for the top level RR, nobody should touch, and I think the same analogy here.
Yeah, RBAC has been an important part of sort of actually making this work at scale. Not the tech, right? Just making a large organization, actually be able to absorb it and feel comfortable that they can sort of do these things.
Another question, I suspect I know the answer. Have you considered, one of the things I hear of is stacking agents, and people in the application performance management space want data, which I see as particularly critical in the cloud for things like packet loss, latency, and jitter between processes per flow, basically. Drawback from your point of view is that's not the space you're playing in, plus it might increase the load of the agent on the system. Comment?
Yeah, I mean, so we do collect a lot of flow data, right? That's used for lots of different purposes, and I'm going to actually go to it leads into my next slide, right? Okay. That other slide was really about policy. How do you do policy? But then how do you sort of do traffic visualization and analytics, right? So number one is a lot of this flow data that comes out, right? And we decorate it based on the labels that we sort of put into the system, so you understand whether this is a dev workload or a prod workload or which application it's sort of part of, and we sort of stream that out. And some people sort of take these into large data lakes. Some people use these for, they apply machine learning and artificial intelligence on top of this to find security vulnerabilities. Some do use it for operational purposes, right? But it is a full east-west traffic flow. Like it is all of the flows between all nodes in your system, right?
It's kind of the holy grail.
What?
That's the holy grail.
Yes, but it is also a lot of data, right? So people need to understand how to sort of absorb this and do it. So then to answer your question, we do look for other ways to sort of augment that data to provide other use cases, but we're not in the APM space. So the other important thing is how do we build, so I talked about global security policy, and I also talked about global visibility. How do we build that application dependency map, right? And so there's a bunch of algorithms that we built to be able to do that. So what happens is each of the PCE clusters actually, what I call is build a molecule of what that map is, right? And rather than sending all the flow data to the master, they build these molecules of these maps, these graphs, and they send those molecules to the leader. And the leader then assembles those molecules into actually a full data center picture, right? And how to actually accomplish that? We spent a lot of time sort of figuring out how to solve the federated map, application dependency map problem. And so then we leverage that. So a customer can come and look at that PCE console on the leader and sort of see that full map.
How heavy is the agent? Is it use a lot of CPU? Not really, as it's doing its data gathering?
Yeah, we leverage what's available in the kernel to sort of do that. We do some aggregation, right? Because we do some aggregation in terms of 10-minute blocks of traffic flows and sort of spool those up. So we try and balance the CPU utilization and the bandwidth used to do that. Because there is I did one calculation where if you really to keep every 5-tuple network flow on all the east-west bandwidth, it'd be like 10%. You'd use 10% of your bandwidth just keeping track of the traffic, right? Yeah. So we do some aggregation to be able to sort of, minimize that.
Is that something that could be tuned though? Meaning, if a particular customer desires more information at the expense of bandwidth and CPU utilization.
Yeah, there's a whole bunch of tuning. Get it faster. There's a bunch of tuning parameters. Yes. Okay, and then I just briefly on data synchronization between the PCEs. We spent a lot of time sort of figuring out some of this. I mean, I talked about the policy can be relatively simple to distribute. Distributing some of the workload information again at full load, right? Can go up to 10 megabytes per second, and then we have security sort of built into this. And then my final slide, so before we hand it over to Matt to do some of the demos, is really the drivers of why did our customers ask us to do this, right? Because that's we're responding to customer demand. It's the need to be active in multiple data centers and have worldwide availability. This is what our customers are asking. They want to do micro-segmentation and having this application dependency map at scale. That's what they're driving us to do, right? The need to support 100,000 active workloads globally. That's the other driver. And then finally, that disaster recovery, right? Being able to do, being able to survive disasters, have a good disaster recovery story is what's driven the innovation in the PCE Supercluster architecture.